We have a great show lined up for you tonight, so don't turn that dial. I've got Dr. Sean McDeavitt in studio with me tonight. He's at your Texas A&M University. We're going to talk about nuclear power, nuclear energy, nuclear science, nuclear engineering, anything with nuclear and anything after that, right? Dr. McDeavitt, how are you doing?
I am doing well. Thank you for having me.
Well, great for you to come down today and share some of your weekend with the listeners. I tell you, listeners, it's going to be a fascinating show. You know, Dr. McDeavitt, we don't talk much about nuclear physics on the radio. It doesn't come up a whole lot. And nuclear engineering, but listeners, I had the distinct honor of getting a tour last week where you showed me around the nuclear reactor.
Yeah.
And that is fascinating, you know. That water is so clear, is amazing.
We certainly purify it to make it safe for operations, and it actually makes it also very, very clear, so you can see 30 feet down to the reactor.
It's amazing, you know. I almost wanted to take a little dip in it, but probably would have been a good idea.
It would have been a bad thing for you,
yes.
And then our system would have had to clean up for a few days.
Yes, it's probably 3 or 4 days because I didn't shower that morning. I was going to move. I had to go move a bunch of furniture that day. So yeah, but anyway, I didn't even know we had a nuclear reactor. So we're going to talk about in this town. We're going to talk about that tonight, listeners. Fascinating stuff, and we'll get to that interview in just a few ticks of the clock. But don't forget, after a family affair tonight, Sean, do you like dance and disco tunes?
You don't want to see me disco.
Well, DJ Lance is here from 7 to 9 to play some dance and disco tunes. 80s music from 9 to 11 with Michelle. And if you just can't sleep at night, listeners, you want some heavy metal, headbanging music, well, St. Patrick, the iconic one, is here in studio from 11 p.m. to 1 a.m. playing his Iron Horse Cafe music, or as he likes to call it, he gives you your Ozzy Osbourne fix at midnight. So there's something for everybody on KEOS, and that's certainly true on Friday nights. Anyway, thanks for joining tonight. Dr. Vance is here. This is our 826th presentation of A Family Affair, where knowledge is never mistaken for wisdom. Anyway, Dr. Vance here on a show we call A Family Affair. We come to you live from the Bell Studios each and every Friday from 6 to 7 p.m., and we're located at 202 East Carson in Bryan, Texas, at the lovely Bell Studios. That's my high-tech bell right there. Anyway, I got Dr. Sean McDeavitt in the studio with me tonight. He is the director of the Nuclear Engineering Center there, Science Center at TMU, the director of the Nuclear Power Institute, faculty affiliate, it says, Energy Institute, and a professor of nuclear engineering at TAMU. So you're busy, it sounds like. Yeah,
you can almost judge somebody's ability to say how often they are able to say no to things by how many titles they collect. I have a number of different hats that I get to wear. So yeah, it's a lot of different things. I am a professor. I am also the director of the Nuclear Engineering Science Center, and I'm the director of something called the Nuclear Power Institute, which a couple years ago was kind of merged into the Science Center. And so there's a lot of different aspects to that. I don't know how much you want me to do that right now, or I can talk about it later.
Yeah, we'll get to it in a little bit. It sounds fascinating. But the bottom line is, listeners, Dr. McDeavitt knows nuclear engineering probably as well or better than anybody in the community. Maybe in the state, you're up there, you know a lot. You've been doing it for a while. And we're going to talk about this subject because it's something that we haven't talked about on A Family Affair before. You don't hear about it much. You know, nobody talks unless there's some sort of nuclear bomb out there. Most people think that's what nuclear physics is, and it is that, but it's much more than that.
I've never built a bomb.
Yes, never built a bomb. Hopefully never will, right?
No, that's not what I do.
No, not what you do at all. Anyway, listeners, so we're gonna find out all about that tonight. To begin with, set the stage for us. You know, where'd you grow up? Where are you from? And how'd you wind up at Texas A&M?
Sure, yeah. My background, I grew up in central Indiana. You know, it's a little more complicated than that. My family moved around a lot, so I was born in West Virginia, lived in Pennsylvania. 3 years old, I was in Indiana, a place called Crawfordsville. It's where Dick Van Dyke grew up, too, apparently.
Oh, really?
I never met him. But in that area, I grew up, and then about 11 years old, my parents split, and then I moved to Noblesville, Indiana, about an hour away. That's where I went to high school, and
is that close? How's that just to South Bend?
If you south of South Bend,
Notre Dame, you know.
Yeah. But I went to Purdue, so we hated Notre Dame. But I don't hate anybody right now. But the point is, Noblesville. If you look at the square of Indianapolis, we are on the northeast side of Indianapolis, and that's where I went to high school. It's where I met my wife, who became my wife. We're a couple weeks from now. We're hitting our 35th wedding anniversary.
Wow! Congratulations!
And so
that's amazing.
She is amazing.
Yeah. Well, 35 years that's awesome.
And so as we look at what we're up to from there, I went to Purdue University. I went straight for nuclear engineering. Went into the nuclear engineering program as a freshman, and 4 years later, I got my bachelor's degree, but I stuck around for another 5.5 years, got a master's and a PhD, and 2 children. And
so that was a busy time period. It sounds
we got married and had 2 children. I often say that's how I learned how to run major programs with budgeting. And then I went to Argonne National Laboratory in the Chicago area, and I worked there for about 11 years. And then shortly after that, I went back to Purdue for a short stint as a professor, and then I landed here in Texas A&M in 2006, and I've been here for about 15 years this August.
Awesome, man. What a background. Now, growing up, Sean, was nuclear energy, is that something that you were fascinated with as a child or a kid, or just science in general, or no?
I mean, I was good at math. I was good at science. I enjoyed theater. I enjoyed music. I played the saxophone. I tried to play every sport that there was. I was pretty bad at it, but I did enjoy life as a kid, basically. And it was around my junior year, really, as I was starting to think, okay, now it's time to think about college and things like that, and what am I going to do? And so I thought about going into acting. I thought about going into law, and I thought about science and stuff, and a couple of different influences that drove me toward nuclear engineering, but not really, I would say, a well-thought-out decision. It just actually turned out to be exactly what I wanted to do, and I still enjoy it.
Yeah.
A lot of people, when they reach that stage of making a major life decision, they make it with very little information. And I was one of those. And so you could say I picked nuclear because it sounded cool, but it's got more detail than that. In high school, I took AP Physics, and we did about 2 weeks of radiation chemistry, and that fascinated me. I wrote a term paper on fusion, and so certainly coming out, I had a idealistic, I'm going to change the world, and I want to go and do good things for humanity and the culture, and it happened to be cool, and I wanted to learn more about it. A couple other influences. One's kind of weird, but the whole 3 Mile Island incident happened around the time I was 11 years old.
Now explain for listeners what that is who maybe don't remember that.
Okay, in Pennsylvania, 3 Mile Island it's in, I forget the name of the river, but there's a river and there's an island in the middle of it. Had a set of nuclear power plants, and one of the units had an incident where the core was molten and released some hydrogen. All of the energy, thinking back of it now as a professor, I want to make sure I tell you that all of the safety systems worked, and there was never a release of consequence to the public. But it was a pretty intense environment, and I remember wondering what it was. So that's all the point there, was that while that was going on, I was 11 years old, and I saw the news. Jimmy Carter was there, and other people were going on, and they were talking about hydrogen explosions that never happened. But and now you go back, if you look at the old footage, there are pictures of mothers talking to the news cameras with their babies, and they're covering them with blankets to protect them from radiation, which would not have worked. But that's neither here nor there. When you're terrified, you're terrified. Right. And so there was a lot of public fear there, and so in that time frame I got fascinated. I was interested in it, and then shortly after that there was this movie called The China Syndrome. I don't know if you ever saw that.
I remember the name.
It was a fairly anti-nuclear movie. It was trying to prove why nuclear was bad. It starred Jane Fonda, Jack Lemmon, and the guy who now he makes a lot of big movies. I forget his name, but he was in it, and basically that movie, when I saw that, I was like, it explained the nuclear fuel cycle, it explained nuclear power a little bit, and maybe imperfectly. I've never gone back to rewatch it, but I was fascinated to say, I could do that. And so in the midst of that, maybe this movie that was trying to convince people to stay away from nuclear brought nuclear to the forefront. Michael Douglas was the guy.
Okay, yes.
Yeah, so that was back when he was still just Kirk Douglas's son.
yes.
But that movie had an influence on me, and so as I was looking at college, somebody said, you should look at engineering. I had no idea what it was. But it was I'm merging math and science. Oh, yeah, that sounds good. So I looked at it, and I got the application information from Purdue University. And, you got the list of electrical engineering, mechanical engineering, civil engineering. Down at the bottom of the list was nuclear. I said, that's me.
Yeah.
It wasn't because of a fascination with nuclear science. I certainly have a bit of a personality of liking to do that weird thing that nobody else wants to do. And so all those different influences made it a positive for me. But it was attractive. There was just a draw, almost a calling. I wouldn't go so far as to say it was this deep felt call, but it certainly drew me. And once I took my first classes, I never looked back.
Never looked back.
Yeah.
When you got your PhD and in nuclear engineering?
Yeah, and nuclear engineering is a broad category. There's the people that do computer stuff all the time. I call them the code warriors. And then there's the people that like to do energy transfer, more how do you cool the reactor, how do you sustain the power level and generate the electricity. And then there's other fields like nuclear security and other activities. My specific field of interest was material science. So by the time I finished college, I had nuclear materials, so nuclear engineering degree with understanding the basics of nuclear energy. I also did a lot with understanding the basics of material science. And then I went to work with a bunch of chemical engineers, so I had kind of a nuclear materials chemical engineer background. So I tell people that I can pretend in 3 areas. But that's kind of the basis for what I have. And so when I came out of Argonne to be a professor, I started building this thing I call the fuel cycle and materials lab. And we have a lot of different research dealing with nuclear fuel development, manufacturing new types of nuclear fuel, doing nuclear fuel testing, or we also have some nuclear topics where we deal with creating systems for nuclear reactor systems. And there's just a lot of different things that we do, but it's very much focused on nuclear materials. So I work with uranium a lot in various forms, and we manufacture and test and measure the behavior. I also work with nuclear waste some. In fact, back at Argonne, that was my principal job, developing forms for nuclear waste to be disposed of safely and understanding what that means.
Right.
And then back in 2014, I answered the call here at A&M to become the director of the reactor, and that's the 1 megawatt trigger reactor that's out by the airport.
Right.
If you ever take off or land at the Easterwood Airport, you've got Disaster City on one side and a nuclear reactor on the other. And that reactor is at the end of the runway, around the way. It's very much at the end of the road.
Yes.
A lot of people in town don't know it's there.
I didn't know it till I talked to you. Yeah.
But it's a useful facility, and it's been there since 1961 was its first criticality. We're having our 60th anniversary party this year. And then about 2 years ago, I took on something called the Nuclear Power Institute as well, which is a workforce development program across the state of Texas where we interact with high school students, and we're encouraging them into STEM education fields and just understanding what that is about. Yes. And so that's like the very, very short, skipping a lot of detail answer to who am I and where do I come from. And that's not even counting the stuff that I think is even more important, which is my family and the extended part of me that's really who I really am. So
yes, well, that's awesome. Again, listeners, this is KEOS 89.1 FM, College Station in Bryan. Show we call a Family Affair. Dr. Vance here with Dr. Sean McDeavitt here from Texas A&M University. I guess we say howdy or whoop, whatever it is.
I can whoop.
There you go. And we're talking nuclear engineering, nuclear science tonight on a Family Affair. Dr. McDeavitt, for the layperson out there, go back to the basics. What is nuclear fission? I mean, it's a very scary sounding term, intimidating sounding term, but it's really not. What is it exactly?
Well, when you say the word nuclear, what you're dealing with is the nucleus.
Right.
So if you're an engineer, you use math and science to solve problems. With you're a nuclear engineer, you're using math and science to solve problems with special attention to phenomena that happen in the nucleus.
Nucleus of an atom.
And so if you look at an atom, the basics before quantum physics made things a little more complicated and we understand more particle physics than we used to. But, it's protons and neutrons are the nucleus, and then there's the electron cloud. I'm not going to go into the depth of it with the muons and the neutrinos and the other things that are physically real, but but basically you've got this nucleus that is easy to understand when you think of it as a combination of protons and neutrons. These little microparticles that's on the order of 10 to the minus 15 meters in size.
Very tiny.
That's really tiny. We can't see them.
Not even with electron microscope.
No, electron microscopes can get down to 10 to the minus 8, maybe. You get down that range. So we're far, far, far below that.
So although we can't see them, we definitely see their effects. So
yes.
Yeah, so the nucleus, so everything out there are made of atoms.
Yes.
I mean, clocks, TVs, wood, everything, right? Human body.
It's like that old joke, you never trust an atom because they make up everything. And so...
Yes, that's true. They do. So inside every atom of everything has a nucleus of protons and neutrons, and then there's electron particles called a cloud around it. And so that's the basic of every atom. So with that, how do you get fission? Where does fission come in?
So when we start with the classes where we start to teach the history, we talk about the discovery of the atom, we move to these things, and you look at the atoms in the periodic table, and you go from hydrogen to uranium and above. The difference between any box on that periodic table is the number of protons. So hydrogen has 1, helium has 2, lithium has 3, boron has the next... beryllium is 4, and it goes on up to uranium has 92 protons. But it also has about 144 neutrons, and the neutrons are, when you bind the protons and the neutrons together into a nucleus, they are held together by a particular binding energy. The heavier atoms like uranium, if you can induce them with enough energy to cause that 92 plus 144, about 235, I'm not sure if I gave you the right numbers to get to 235, but you have the one with 235 protons plus neutrons. Then you add a neutron, it becomes 236, and then that's got enough energy that's input with Einstein's E equals mc squared that it actually is more stable to split into two, and you actually release energy by doing it. But when you think about energy, all you're really doing is moving downhill. If you pour a big bucket of water on the top of a hill, it's going to flow downhill. If you put a big rock on the top of a hill, it's going to roll downhill. By putting an extra neutron inside of a 235 uranium nucleus and it goes to 236, you've basically put it at the top of a hill energy-wise, and it tries to get to stability. And by one of the ways it can do that is to split the atom and kick it into two other atoms.
Okay.
That's fission.
That's fission. So atoms want to be naturally in a stable state,
yes,
right? And that's sort of the way God made them, just the way it is, right?
The whole subject of radioactivity is all about stability. The whole reason you're throwing energy out of a nucleus is because it's unstable and it wants to be stable.
So the theory that Einstein came up with is that M E equals mc squared.
Yes.
That seems so complicated. It's basically the idea of if you split the nucleus of an atom, an unstable atom, like uranium-235 that became 236, and it splits into two, then that causes a chain reaction, right? The more neutrons get shot out, so it just goes on like that, right?
That E equals mc squared, the equivalence of mass and energy, is a fundamental principle of physics now. We understand it now. It wasn't necessarily understood in around the 1900s or before, but now we understand that you can take matter and turn it into energy and energy and turn it into matter. It actually becomes a great MacGuffin in science fiction, things like Star Trek, so they didn't have to pay for the special effects to land a spaceship on the planet. They could just twinkle and land by a transporter. Interesting fun fact, though, if you do E equals mc squared and calculate what the mass of a human is, the amount of energy that would require is more than it would take. I remember I did the calculation. You could power my house for like 1 million years or something like that. It's
really?
A massive amount of energy.
To have a human theoretically
completely turn into energy.
Yeah, turn into energy and then materialize back, I guess, to hopefully.
Assuming the soul follows, but that's a whole different metaphysical story.
I don't lose my soul along the way.
But the point here now is with the E equals mc squared, it applies in multiple directions, but it gets applied here because there's an amount of energy that is holding that nucleus together. Little fun fact, if you were to, we can't do this with a balance, but if you were to measure the 92 protons and all of the neutrons separately and add them up, and then you were also then to measure the nucleus, the individual components weigh more than the nucleus.
Really?
There's higher mass. It's called a mass defect. And when they weigh more, what you really have is that mass that's missing converts to energy, and that's the energy holding it together.
Wow. This is fascinating. Now, for the listeners, energy is typically in the form of heat, light, or motion, right?
That's the way we experience most forms of energy, but there's chemical energy, there's other forms of potential energy, electrical energy, there's different types of potential energies that you can talk about. But yes, it's you sense energy as heat. In fact, one of the earliest energy units was the candle. 1 candle, 2 candles, 3 candles.
Oh, yes.
And so that now we use BTU. Those of you that live in Bryan especially know that one.
Yes.
And then we converted to science units now that we use, like joules, and that's energy. But then that gets converted to power, and you get kilowatts.
Yeah.
And things like that. So
what you pay for every month on your electric bill.
Yep.
Yeah, so this is fascinating stuff. Again, listeners, this is KEOS 89.1 FM, College Station in Bryan, a show we call A Family Affair. We come to you live from the Bell Studios every Friday from 6 p.m. to 7 p.m. with a fascinating show. Tonight I've got Dr. Sean McDeavitt from Texas A&M University, the Nuclear Science Department over there. He's a professor and also the director of the Nuclear Science Center and director of the Nuclear Power Institute, which you talked about briefly. We're talking everything nuclear science tonight, a fascinating topic. First, I want to give a shout out to Dr. Karen Kirkland, by the way.
Yep.
She hooked us up together, so I want to say Karen, I know she's listening tonight also. Just saw Karen the other night at a Taekwondo class. She almost beat me silly with one of those batons. She's tough now.
You don't want to be on the other side of that.
No. She looks meek and mild, but she can be pretty tough when she needs to be. Also, listeners, we're in the middle of our summer fund drive. If you like shows like this, by the way, where's somebody going to hear a show like this in Brazos Valley? No place else but KUS that I can think about. We'd love for you to give a pledge to KUS for listeners supported. You can do it online safely and securely. Just go to KUS.org, click on the donate now icon. If you're driving around Bryan, you want to stop by 202 East Carson, just knock on the door. We'll come let you in. You can drop some change in the bucket and maybe meet Dr. McDeavitt if you'd like. Or you can call with your pledge, 979-779-5367. We'd love to talk with you. And if you love shows like this, then please be part of this experiment we call community radio. We're here for you. We've been here, Sean, since 1995, I believe, KOS, doing what we do. We've moved to several different locations, and we're in our Bell Studios, we call it now, because we bought it from Bob and Judy Bell back in, maybe 10 years ago now, something like that.
So it has nothing to do with the bell in the corner over there?
Nothing with the bell in the corner, although that's kind of our theme, so you'll see bells throughout the studio if you walk around here a little bit and look at it all. And occasionally I ring my bell over there just to show that it is the Bell Studio. But we're 202 East Carson, and we're KEOS 89.1 FM, College Station in Bryan. Okay, so we got to the point where we know that when you get to an atom that's heavy, like uranium, has 235 protons and neutrons combined, right? And if you shoot, somehow you have an unstable atom that's one to emit a neutron. Is that right? You can line it up somehow and aim it, and So how does that work?
So you've got the difference between fission and fusion. We can talk about fusion.
Yeah, what is the difference? I'm curious.
Fission happens. Well, hypothetically, if you're a physicist, you have to say that fission is possible for anything. But fission happens naturally as an energy that goes into rolling downhill, where the end state has a lower total energy than the beginning state because you've converted it to kinetic energy or something like that. That's fission, where you take one big atom, add a neutron, make it unstable, and it splits. And those two fission products go off and travel with a lot of kinetic energy, which then bounce into the atoms around them. When it bounces into the atoms around them, it actually causes them to vibrate. And if you vibrate an atom, that's actually the phenomenon that causes heat.
Okay.
So if you think about a physical, like if you touch the countertop right here, it feels cold. It's basically sucking heat from my hand as it's taking the heat in my body into the body of this table, and then somebody else could come along and that table's warm. So I basically just made all the atoms in this countertop vibrate at a slightly higher frequency because of the heat. And that's what the fission does, is it splits and causes the atoms in the crystal structure to heat up. because of vibrations. You're taking energy from the nucleus and translating it to the lattice of the atoms, which is then causing it to be temperature, which is then taken to the water, which is then driven to a steam turbine, which is then making a turbine turn, and you make electricity, and it comes out and turns on your coffee pot.
Yeah, that's fascinating. So basically the heat that from the vibrating atoms can actually heat up water, could cause steam, for example. I guess they could turn a turbine or basically a magnet or whatever that makes energy, and then hook it up and send it to your house, right?
Yeah.
So that's how it works.
Now, just to get back to the question you just asked so I don't lose it, the fusion is on the other side. What I mean by the other side, fission tends to happen naturally on heavy, big elements like uranium, neptunium, plutonium, americium, curium, those big actinide elements. You go down to hydrogen, one proton and sometimes neutrons, but mostly it's the one proton, and then you got helium with two protons and two neutrons. If you take those atoms and you force them together to make a bigger atom, that's actually the reverse, where you actually now have energy released because you take those tiny atoms, make the bigger atoms, and there's less mass after because of it that causes energy release. It turns out that the ability to get those nuclei, that's the way you say it, you get the nuclei together, it takes an awful lot of energy. So you have to have this fusion reactor that gets the atoms moving at temperatures on the order of the sun to actually overcome the positive on positive repulsion. So you got to overcome the repulsion force, and you get those atoms to come together, and you can cause them to fuse, and they will release energy. You get it done on a high enough energy scale, a number per second, and you now have the ability to generate energy. We're still working on that one.
It sounds like that would be more complicated or more difficult or more. It sounds like fission would be more efficient. Just hearing you talk.
Fission is this may sound counterintuitive to some, but it is somewhat simpler. And what you need to do to get it to fall into a lower energy state by generating energy. Fusion takes a lot of work to get there, but it does have the potential to generate energy.
Now, like, for example, a star like our sun, is it a fusion or a fission?
That's fusion.
That's fusion. So it's burning hydrogen, I guess, or
yeah, I think it's mostly hydrogen, and it's basically taking the hydrogen, making helium, and the fusion reactions that are happening there. It's got a fuel supply of hydrogen and helium in the sun, and it's just burning.
It's burning for many, many, many years. I guess
got a while to go.
Now, eventually, theoretically, it would burn out, right? Theoretically, at some point. I mean,
that's when
billions of years.
You watch shows or you hear people talk about, it's a limited fuel supply,
right?
And so you can do a calculation that says if it burns at this rate, it goes out to some mind-numbing number that none of us will ever see. But hypothetically, if you go into science fiction space, people like to envision what happens when the sun dies or something like that. But that is a number that is bigger than reality in my brain.
We don't need to worry about it in our lifetime, I guess.
No, or
our kids' lifetime.
Many generations' lifetime.
Well, but it's interesting because stars do die.
Mm-hmm.
They found evidence of that in the solar system, right? Isn't that basically what happens? Because suns are stars, right?
I'm not an astronomy expert, but when you look at all the different phenomena out there, there's a lot of fascinating things, and you can see different points of life cycle in the stars out there.
Yeah. It's fascinating stuff. So back to radiation now.
Sure.
What listeners don't know, and explain this for us, there's something called, background radiation, for a better term. Just walking around, we're all exposed to radiation every day, right?
Everybody has an exposure to radiation no matter where you are. You cannot hide from it because some of it's coming from within you. Every human being has some natural radioactivity that's associated with their body.
Explain how that works. Like the cells, there's not fission going on in your body, is it? Or
well, the nature of what radioactivity is you have some kind of an isotope element that has activated to the point of being unstable, and it's got something called a half-life. So at some point, that unstable atom will naturally give up its instability by kicking out a particle. It could be something called an alpha particle, which the big ones do, and that's 2 protons, 2 neutrons. Or it could be a beta particle, which is like an electron, or it could be a gamma ray, or sometimes it's a combination of both. So in your body, you have carbon-14. just a little bit. But
it's in your cells,
there.
all your cells, right?
That's when if you hear the concept of carbon dating.
Yes.
So if you assume a certain concentration in a body when it's alive and then it dies, it's got about a 5,000-year half-life, a little bit bigger than that, but you can calculate by this formula how long ago since something was at that level. And so carbon is present in everybody. And then there's other radioactive isotopes that are just part of our nature. One of the big ones is potassium. Potassium-40 is the natural, that's all potassium is radioactive.
And that's in our body too.
Yeah, it's in your banana. It's in your orange.
Yeah.
And if you eat a lot of citrus, you're going to be consuming potassium. If you have a low sodium diet, so you switch to potassium, you're consuming a radioactive material. It's a low level radioactive material, but it is part of your nature. And at the same time, you go outside and you're exposed to cosmic radiation coming from the sky, and you're exposed to natural background radiation coming out of the ground, and all different types of sources. And so, the people are much more exposed than they think they are. So, but then they start to, like I mentioned that banana thing to people, and I've had people say, well, I'm never eating a banana again. That's kind of the wrong response.
Right.
And so I have this way to explain it that I sometimes use, because there is the math number, just like we use feet for distance and joules for energy. There's something called a sievert for radiation exposure, or radiation coming out of something. So a sievert doesn't mean anything to most anybody. It barely means anything to me. But effectively, you can take that sievert and convert it to bananas. How many bananas does it take to equal a certain amount of sieverts? It's about a 2-to-1 ratio on that. So you can say that the radiation dose that you get from, basically, if you're married, you sleep in a bed next to a human being all night, it's about the same level of radiation exposure from that other person as about one banana.
Really?
Just a little bit less. It's like you're eating a banana every night. And I don't even like bananas, but that's a different point. But then if you go get a chest x-ray, it's almost the same level of exposure as if you're getting 50 bananas.
Okay.
And then if you fly from New York City to Los Angeles, you're exposed to more radiation because you lose 30,000, 50,000 feet of shielding. And so it's about, you get about a 50 banana surplus dose. And so that's kind of in the order of 1 to, not quite 100, but 1 to 100 bananas is about normal, what you're exposed to.
On a regular daily basis,
Yeah.
It sounds like.
Even a little bit more.
Which isn't harmful. It's
No.
just there. It's part of our life. Now, what about the sun? We talk about skin cancer. The radiation can hit our skin.
Yeah.
So you can get a high dose of, is that radiation that does the damage?
Well, when you get to the UV radiation, that's a form of radiation. It's a photon, but it's not nuclear.
Okay.
It's not in the same category. Or in a microwave, people talk about nuking their food, but there's nothing nuclear. It's a resonance at the atomic level that happens, or magnetic resonance imaging, where you go get
an MRI,
get a scan,
for example.
an MRI. That is something that's resonating with your nucleus, but it's not nuclear radiation.
It's not fission or anything. It's not an isotope. It's simply.
Yeah.
But so, what about when you go get the like I had a nuclear stress test one time. They injected an isotope or some sort of dye. What is that?
Yeah, I've had that done. That's an isotope called technetium-99, and it's made in a nuclear reactor. Actually, if we didn't have nuclear reactors, we would have a much smaller supply of that, and we couldn't do those stress tests. But what that is it is what's called a beta emitter. It gives off a gamma ray and a beta particle, but that gamma ray is what gets detected. So it's injected into your blood. They make you walk uphill for about 5 minutes and sweat and feel really tired. And then they go and lay you down on a gamma detector, and it's detecting the gamma rays coming out of your heart. And they use that detector to map the blood flow through your heart arteries, because they can actually image it and see it. And so if there's a blockage, they can see that it didn't make it through or something like that.
Yes.
So they're observing the flow by placing a radioactive isotope in a location and then using a detector to image it so that they can visualize what's happening.
Fascinating stuff. For the listeners, what is an isotope in layman's terms? Explain
All right.
that.
Isotope is, it just means let's explain it this way. Most everybody knows what the elements are,
Right.
the periodic table. If you take the periodic table and stack it up from 1 to 100, and vertically, and then you take each one of those and you stretch it out on another axis by counting number of neutrons. You can have something with the same number of protons, but it has different numbers of neutrons, and that makes it an isotope. And so, for example, hydrogen is most often the one proton, but it also could have a proton and a neutron. We call that deuterium because it's rare enough it's got its own name. If you add another proton, it's called tritium, and then never really see anything above that. But then you go up to sodium. It's got 5 or 6 isotopes, all of them with the 11 protons. I think it's 11. And then there's multiple different numbers with numbers of neutrons. You go to oxygen. We breathe oxygen. You take a deep breath right now. Most of the oxygen that just went in your body is oxygen 18, which means it's got so many protons, so many neutrons. But sometimes it's 19, sometimes it's 20, sometimes it's 16, 17. So that's what we mean by an isotope. And if you get off nature, the stuff that you can dig out of the ground or breathe in the air, the natural, stable isotopes, if you somehow get to a point where you have too many neutrons or too few neutrons, that's unstable. And so natural process says, I got to be stable. And so that atom wants to kick out radiation. So you might kick out an electron or a positively charged electron called a positron, trying to get to stable.
It does that automatically. You're not thinking, I'm going to kick a neutron out.
No.
Each cell in your body just does that.
It's a very thoughtless process. The nucleus just does that naturally, just like if you were to step out of an airplane, you're naturally going to move toward the ground.
Right.
It's that kind of a nature.
Isn't that fascinating? Listeners, again, you're just tuning in. We're talking to Dr. Sean McDeavitt from Texas A&M University, Nuclear Science Department over there, Nuclear Engineering. Fascinating subject tonight on nuclear science in general. There's so many facets to it. Nuclear energy, it's safe, right? I mean, listeners, for the reactor you mentioned out there, talk about it's very cool, by the way, to look at, but it's very safe. It's nothing for anybody to worry about. It's very beneficial to the community also.
Everything that we do as humans carries a certain amount of risk.
Right.
And yet, if you look at the safety record of nuclear power, it's very, 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 very good. And so, I believe it's safe. Most people would not build a house that they know could maybe 50% of the chance fall in on top of them.
Right.
And so we don't take that risk. And so this is also something where the nuclear power, there's a lot more than we have time to talk about. And you mentioned Karen earlier. Actually, that's one of her fields of expertise is nuclear reactor safety. But it is certainly a safe technology, and the big incidents that you hear about, like Fukushima or Chernobyl or 3 Mile Island, they have root causes that are understandable and fixable. Like, for example, we don't have a communist system that governs how we run our nuclear power, so Chernobyl won't happen here. When Fukushima, we're not going to have a 45-foot wall of ocean coming on our nuclear power plants in Texas right now. So there's different things that exacerbated those problems. And at the same time, I could talk through each accident and talk about actually step by step what happened. But in general, the 96 power plants we have operating in the United States are generating 20% of our electricity.
96 power plants across the United States.
Yes. And we have 2 more being built in the United States, and there may be more to follow. And there's a whole push towards designing smaller, it's kind of a leaner, meaner kind of technology where you can deploy small things and you can do more of them in different locations. Those modular reactors are under design, so there's a very, very, very significant safety record. You compare the safety record of air transportation, or especially road transportation. More people die on the road than have ever died at a nuclear power plant. Actually,
by
nobody.
far.
But we're down to 0 at the nuclear power plant, except if you get into the defense industry, and then you might be 2 or 3 people. And so. But people are they feel comfortable with the risk of driving a car.
Sure.
We understand it. We can touch it. We can see it. We know it's up to us. Something that we don't understand gets to be scary, but there's a lot of other things we don't understand that also carry risk, engineering risks of things, but the health risks of nuclear power are managed and real. I mean, there's a reality to it, but there's also a reality to how improbable it is. I'm not trying to say it's never a problem. And one of the things people like to ask me if they get into a Christmas party conversation or something is, well, it almost always comes up, what about the waste?
Yes.
And that's actually an area of expertise that I have had for a long time, and we know what to do with the waste, but it's more of a social and political challenge to get things positioned correctly.
Well, where do we talk about the waste? Because every fission process, I guess, it's not perfectly efficient. There's a little bit of waste, right?
Yes.
Which is, I guess, extra atoms or extra particles or something is waste, and it can be it can contaminate. It has radiation to it. And it has a long half-life. It lasts a long time. So what do we do with that?
So this is where I was looking at my watch saying, how much time do I have? Because you get into this discussion of nuclear waste, and there's really different types of nuclear waste. And so we'll get to the fission and the fuel in a moment. But before we get there, you mentioned the stress test, the Tech 99. The needles that were injected into your body were hazardous waste, and they were nuclear waste. So there's medical waste with radioisotopes. There's different things from if you work in a laboratory and you're working with different types of isotopes for whatever reason. We use phosphorus and carbon and other isotopes. We manufacture isotopes at the Science Center for petroleum industry to image fracking cracks, for example. That has nuclear waste associated. But there's low-level nuclear waste, and there's classifications within low-level waste from class A, B, C, and beyond. And then there's other types of waste that involve our weapons facilities, plutonium-bearing waste. That's another category. But now, having said all that, to just hint that it's a big topic, let's talk about nuclear fuel. A nuclear reactor, let's just say we pick on STP down by the Gulf or Comanche Peak up by Dallas. There's 4 nuclear reactors, two each. And they take a nuclear fuel assembly. And the nuclear fuel assembly is about 200 rods, about 12 feet tall, arranged in a square, and that gets placed in the reactor. It goes in the reactor, sits there for 3 years. No emissions. If you look at a coal plant, I remember being on vacation and watching the trains carrying the coal to a nearby coal plant. It was like 2 or 3 mile long coal car. Right. And they roll in and they roll out with ash, every day. And then in that ash, they're actually liberating some radioactive waste because of the carbon. And there were a couple of other isotopes in that. They actually release more isotopes from coal fire ash than we do from nuclear power. And so nuclear energy is effectively zero emissions. And when you're done with that fuel, basically you've burned out all the uranium you've placed into it. It never leaves the water for a while. It comes out and goes into a storage pool and cools down for a couple decades. And after it's cool enough, they take it and they put it in a can and they close that up and store it. And if you were to pack up all the nuclear waste of that type in the United States, let's just use an analogy here. This would be a really bad idea, but if you could stack them side by side, close packed as far as they could go, put them on a football field, start at the end zone, the end of the end zone, you by now be at the middle of the first 20-yard line, maybe 25-yard line.
Really? That's it?
That's a heavy amount of material. That's a ridiculously unsafe amount of radiation to stand next to. And it would be a nuclear problem. But that just illustrates the size. It's not a huge volume. It's not emitting emissions, but it needs to be packaged away with shielding until the nation as a whole makes a decision on whether to do something called reprocessing, which would be chemically breaking it down and pulling the good stuff out, or just putting it in a deep hole in the ground. Or leaving it right where it is in the can, sitting on the surface. So
right now, it's typically kept in some sort of storage centers around the country, in these very safe cans, as you call them.
Yeah, these cans, which if you ever see the pictures, that you can't walk away with them. They're probably about 20 to 30 feet tall, close to 20 feet diameter, maybe a little bit less. And actually, that makes them 40 feet tall. But we're talking about tons and tons and tons. You cannot pick it up. And even the device that they use to move it from place to place is a monster with, big wheels and a big crane. And it takes hours to move it 10 feet. Something like that.
So nobody's going to pick it up and take it somewhere and open it up right
And
there.
even to break it up, it would take hours to undo the welds and cut through the steel and all the different things. And then when you got it, there would be very little value to you except for perhaps some terrorist who wants to make a dirty bomb, but they could not make a nuclear bomb out of it.
Wow. Fascinating stuff. Again, Dr. Sean McDeavitt with me tonight from your Texas A&M University, the Nuclear Energy Department. You've got a big event coming up.
Yes.
I want you to get to that, and we'll promote it some more as time gets closer, but it's for the community. Talk about that a little bit.
So 1961. That was the year that the first criticality was achieved at the reactor. So 1958, they approved it, the Board of Regents, and then they started the building process. A guy by the name of Bob Cochran was the director of the Nuclear Engineering Department at the time. First director of all. He was kind of the heart of everything we grew out of. And so 1961 was the first criticality. What is criticality? Often, again, I like to point to entertainment. You hear the phrase, the reactor is critical, and everybody starts running and the music's playing. That's really a boring situation. Criticality is the point where you've reached stable power. You're making as many neutrons as you're consuming, and you take it to go critical, you hold it at critical, and that's where you make energy. So it's about as tense as yelling that the light bulb is on.
Yeah, not very intense.
But that first criticality was a milestone in December 18th, 1961. That's 60 years ago. That was actually 3.5 years before I was born. And as we say, anything that happened before you were born was a long time ago.
Right.
So that reactor was built a long time ago, but we're hitting the 60th anniversary this year. And so this year, with the merger of the reactors and the workforce team, the Nuclear Power Institute, we're holding a pretty big celebration where we're going to have VIP dinners, we're going to have a tailgate party. We're also going to have a public celebration fiesta day where we haven't dealt out all the details, but we'll probably have a big tent, and we'll be running reactor tours and just trying to highlight the reactor and let the public know a little bit more that we're here. Because as you said to me earlier, nobody really knows we have 2 nuclear reactors here in town.
Yeah, I didn't know. I didn't have a clue.
And I in the last several years, I've learned a whole lot about licensing and regulations and regulatory stuff. So we have a lot of different things we can talk about with the public in these tours. But as you said, one of the highlights of the tour is you get to come in, see we have a pool that's about 100,000 gallons of water, actually a little bit more than that. And it's ultra high purity water,
crystal clear.
And if you had jumped into it, it would have sucked the minerals out of your body.
It didn't fall in.
Would have been less healthy than a nice, cool, refreshing dip in the water, because water dissolves everything. Yeah. And so we try to get all of that out of the water. You
know what's fascinating, though, also what listeners can see if they come on this tour, remember the blue sort of wave that you showed me in the water. Mm-hmm. Talk about that. That was really cool.
Well, when the reactor's running underwater, there's a blue glow.
Yes.
There's a blue glow that's associated with the reactor.
It's really beautiful looking.
And usually people ask, where does it come from? So this blue light, it's actually a visible blue. It's called Cherekov Radiation. And what it is that when fission happens, we've talked about the fission products, but we didn't talk about all the other junk that comes out. In a nuclear reactor, I like to call it nuclear shrapnel, the leftovers of the fission process. One of those leftovers is some high-speed electrons. So these high-speed electrons are traveling out of the reactor. They're part of the decay process. They're part of the natural part of blowing these atoms up and what's left behind. But they come out and they're traveling at faster than the speed of light in water. You got to make sure you get that in water, because the faster than the speed of light in a vacuum is that physical constant that right now science says we cannot exceed.
We go back in time or something.
Who knows what happens?
Whatever,
Yeah, but if you go to underwater, there's a medium effect on the speed, and so there's a knockdown in the maximum allowable, comfortable, physical, whatever you want to call it, speed of light in water. And so, again, energy falls downhill. You have an electron that comes out of the reactor at a speed that is unnatural. What's it going to do? It's unstable. It gives up its energy. And at the quantum level, this is quantum physics, so it's not like if you're driving and you need to slow down and you can see every speed from 60 to 0.
Right.
It just jumps out all the energy. It just throws a photon out. It throws an electromagnetic wave out. Throws a bunch of different types out, but one of them happens to carry the energy frequency of blue light. So that emanation of the electron trying to go stable is blue.
Beautiful looking too, fascinating. I tell you now. Tell the listeners when that's going to be. Is there a date set for that exactly yet, or are you still working on the details?
The date on the festival day, I think it's in the October timeframe.
And there'll be a way for the public will know how to register or how to sign up for it.
Yeah, we'll have it on our website. If you go to the Nuclear Engineering and Science Center's website, we're in the process of revamping it and getting it there. It's also on the Nuclear Power Institute website. We've got that. And with the Nuclear Power Institute, we've got a YouTube page. We've got different podcasts and other programs that we have done, so you can kind of get a chance to see the things we're doing. Interviewing some interesting people, for example, from the Department of Energy or some of our high school students around the state, just different things like that. And we have a lot of that information, and then the celebration is there as well.
It's going to be a fascinating event. I encourage the listeners to look forward to that. We'll be announcing it also. You'll get me a flyer when you get it all set up. We'll be talking to people here on KEOS about it. I'll probably try to come out there again. I wouldn't mind seeing another tour. That was really awesome.
It's hard to get all the knowledge in one tour, right?
It really is. It's a fascinating tour, and it's something that you don't see very often. So if you have a chance, listeners, and the thing I love about it, Dr. McDeavitt can explain it in terms you can understand.
I try.
So it's not like you're going, what? It makes sense. Hey, we're about out of time. What's closing up? You got a minute or two. What do you want to leave the listeners with tonight?
Oh, I have no idea. I talk too much. We didn't even get a chance to talk about my laboratory where we do the uranium work. But I just would say, when you think about nuclear, don't think of it as something to be afraid of. It's often people's minds go to conspiracies or somebody's hiding something. I don't really think as humans we're really good enough to hide anything. But those of us in the industry, we really do try to do a good job. We really do try to be safe, and we work really, really hard at it. And so I would encourage, if you are interested in this area, pursue it. Yeah. There's a lot of opportunity there. And again, like I said, I've got a life outside of nuclear, but that's what we're here to talk about. And so there's a lot of different things that I could wax on. This is the family affair.
It's a family affair, it is.
We didn't talk about my family.
Well, I know we talked about your wife as one of them. We said that.
Well, we have 5 children and 10 grandchildren.
Oh, my goodness. That is awesome.
Or almost 10, yeah.
That is awesome. Mm. Well, congratulations on that. And coming up on your 35th anniversary, too.
That's
wedding
correct.
Anniversary,
on
you said?
August 9th.
August 9th. That's just a few weeks away, about a month or so. So, Dr. McDeavitt, thank you so much for taking time to come down tonight. And this is a fascinating topic. And listeners, this is what we do on a family affair. We bring you topics that you don't always hear other places. You can't find out this information other places, and KEOS brings that to you. So if you want to donate to us and like what we do, hey, 779-5367-979-779-KEOS, or go to the website, KEOS.org, and click the Donate Now icon, and you can give. And if you like the show like this, if nothing else, call up and say, hey, man, I appreciate the information. It was very fascinating. Dr. McDeavitt, you be careful, and thank you so much for what you do, and thanks for sharing your expertise with us on the family affair. It's awesome tonight. Listeners, do not turn that dial. DJ Lance is up next with some great dance and disco tunes. So we will see you next week on another exciting installment of A Family Affair.